Okay, let's continue in Module 11 with our simple linear regression model, and let's talk about something called the coefficient of determination. We want to ask the question, how well does our regression line fit the data? That is, do we have a good fitting relationship? One way to do this is to calculate something called the coefficient of determination, which is also called R squared. And yes, the R in there is the same R as the correlation coefficient, which we learned about much earlier. I'm going to use a graph here to explain the coefficient of determination. It's a little bit hard to follow. Here's our regression equation. And remember, the points on that regression equation will be our predicted values of y given a value of x. Suppose for a minute we didn't have that regression equation. We didn't have this relationship between y and x. And I simply asked you, give me an estimate of a y value. For example, in the regression that we've been doing, where we have grades as our y variable and hours of study as our x variable. If I simply said, without giving you any other information, predict somebody's grade on the final exam, your best estimate would be the mean of those grades. That's why I put a line here by y bar. That would be our best predictor if we had no other information. However, once we have this regression line, we would use the points on the line as predictors of a y value. Okay, keep that in mind. Let's take a particular point right here, right up here. And so here's the y coordinate of that point. Notice if I take that y coordinate and subtract off y bar, which is right here, that will give me this bracketed distance, which I'm going to call yi minus y bar. Okay, you following me so far? This bracketed distance is yi minus y bar. Now, if you look carefully at the graph, you should be able to see that this distance is the sum of two parts. This part right here and this part right here. Let's start with the bottom part. This would be y hat, the point on the regression line, minus y bar, which I have labeled right here. And this distance up here is y minus y hat. So let me write that out as an equation over here. Basically, we've said that this distance, y minus y bar, is the sum of two parts, y hat minus y bar and y minus y hat. I've repeated that equation on the next slide here. Y minus y bar equals y hat minus y bar plus y minus y hat. I know, it's very easy to get all the y's confused here. It can be shown in mathematics that this same relationship holds if we square all of these terms and sum them over all n observations, in which case we have the equation down here. Summation y minus y bar squared is equal to summation y hat minus y bar squared plus the sum of yi minus y hat squared. The term on the left is going to be called SST, which we'll see on the next slide stands for sum of squares total. The term in the middle is SSR, sum of squares due to regression. And the term on the right is SSE, sum of squares due to error, or sometimes called the sum of squares residual. Here I've got all of these labeled as I was just talking about. SST, SSR, and SSE. I'm going to repeat this slide, but give them slightly different names. SST is sometimes referred to as the total variation. That is, it's the total variation of the y values around their mean. And remember, we've said that SST is equal to the sum of these two parts. It's SSR plus SSE. SSR we're sometimes going to call the explained variation. What I mean by explained is our regression model predicts y hat. It does not predict y bar. So the deviation between these is in a sense explained by the location of our regression line. SSE is the unexplained variation. The actual value of y minus the predicted value of y, remember, is what we call our residual, and that's not being explained by our model. So let me go back to our graph for just a second. Here again is the total deviation of y from its mean for this point. We're saying that this part of it is the explained variation, because our model doesn't predict y bar, it predicts y hat on the line. But the residual up here is the unexplained part, the actual value of y minus the predicted value. Now, all we're going to do is take the ratio of SSR over SST. That's going to give us what fraction of the total variation is explained by our regression model. And that is called R squared, or the coefficient of determination. R squared is SSR over SST. You'll notice that R squared has to vary from 0 to 1. Since SST is the sum of these two parts, the largest that R squared could ever be would be if SSE was 0, then SSR and SST would be equal, and you would have a ratio of 1. The only way that can ever happen, if you think of it, the only way SSE to be 0 is every term in this sum would have to be 0, which would mean that every value of y is exactly on your regression line. In other words, if you had a perfect fitting regression line, all the points lie exactly on the line, then there will be no unexplained variation. It will all be explained by the regression equation. Now, let's talk about calculating R squared. There's various ways you can do it. Again, we're going to do it by hand at first, but later we'll show you how to do it on a calculator or computer, because it can be a little bit nasty to calculate. One way to do it is find SSR and SST and take the ratio. And I think it's easiest to find SSR and SST. You could also find SSE and SST, but finding SSE is a little bit more difficult. A second way to do it is just calculate R, the correlation coefficient, which we had in an earlier module, and square the result, and you'll have R squared. First, let's do it by hand. Let's do SSR and SST. Remember, by definition, SST is summation y minus y bar squared. That term should look familiar to you, of course, because that's just the numerator of a variance term. Remember, way back early in the course, you learned how to calculate a sample variance, and this would have been the numerator of that term. If you square this term out and do a little algebra to it, you will find that it's equal to the following: summation y squared minus n y bar squared. If we go back to the regression example we were doing on grades and hours of study, go back to the calculations, and I'll jump back there in a second. SST would have been 35,350, that's summation y squared, minus n times y bar squared would be 6 times 75 squared, and this turns out to be a nice even round 1600. Let's jump back to our regression problem. Remember, I gave you summation y squared here was 35,350, y bar was 75, n was 6, and those are the things you're going to need to get SST. Now, to find SSR, I'm going to give you a shortcut in how to find SSR. The easiest way to find SSR is first find your slope term, B1, which we've already found, and then multiply B1 by the numerator of B1. If you go back in your notes, remember that B1 was 4.807, and the numerator was 250. So SSR is 4.807 times 250, or 1201.75. You don't have to worry about proving this. Just kind of take my word for it that if you take B1 times its numerator, you will get SSR. So if SSR is 1201.75, and we already had SST to be 1600, then SSE has to be 398.25. And we'll need that in some later calculations. Then, how do you calculate R squared? You just take the ratio SSR over SST. 1201.75 over 1600 is 0.751. This is how we interpret SSR. Remember, SSE is what we call the total variation. SSR is the explained variation. So basically, we have the ratio of the explained to the total, or we'll say that 75.1% of the variation in grades on the final exam can be explained by the linear relationship between hours of study and grades. Now let's go back to R, the sample correlation coefficient. You might recall that R varies from -1 to +1. So if I know R squared, can I just take the square root to get R? Well, not quite, because remember, square roots can be positive or negative. How do we know the sign of R? Well, if you think about it for a moment, it's going to be the exact same sign as that of our slope term. If our regression line is positively sloped, well, we're going to logically have a positive correlation between the two variables. If the regression equation was negatively sloped, then we would have a negative correlation. So in our example, remember the slope was 4.807, I believe, which was positive. So R would have to be the positive square root of R squared, which will be 0.866. And that's the end of part 2. And next we're going to go into hypothesis.